Hello, my name is Christopher Lusick, and this is my video lab report for Lab 1, Constant Velocity. For this lab, I developed this problem statement: how the observed position versus time compared to the predicted position versus time of a rolling object at constant velocity. The answer to this question will be interesting because this will display to us how external forces cause differences between predicted and observed data. To complete this lab, I used Newton's second law, the momentum principle, tracker, and GlowScript. First, I'll explain the basics of Newton's second law and the momentum principle. Together, these mean that when there is a change in momentum, there must be a net force acting on the system to cause this momentum change. This can be modeled by the equation F net equals dp dt. This will be very important to this lab because an object moving at constant velocity will have an F net of 0. If the velocity, and therefore momentum, is changing, then there is a net force on the object. My procedures for this lab were to record a lacrosse ball rolling across the frame of my camera. Using the known diameter of the ball, 62.7 millimeters, I was able to find the distance the ball traveled over time using tracker. I then used GlowScript to make a computer model of this situation. Here is the original video of my lacrosse ball rolling across the screen. Using tracker, I was able to track the position of the ball over time as shown here. This produced a position versus time graph along with data points shown here. Using these data points, I calculated the initial velocity of the ball over the first time interval and determined how long the ball traveled across the screen. I then input this data into GlowScript. I input the known radius of the ball in meters, its mass in kilograms, its initial position at the origin, and its calculated initial velocity. The time step was 1/30th of a second because this was the time between frames in my video. In the next section, I input the time to be less than 0.933 seconds, as this was the total time the ball traveled across the screen from tracker. Since the model will have the ball traveling at a perfect constant rate, the net force is 0, and the velocity will continue to be 0.85 meters per second in the x direction. When I click Run, an ideal computer model of the situation is shown. I get a position versus time graph and a velocity versus time graph with data points, shown here. As you can see, velocity is constant. I use the observed data points from tracker and the model data points from GlowScript to compare the position versus time of both, shown in the scatter plot here. The predicted position versus time graph has a slope of 0.85 meters per second as the velocity is perfectly constant. However, the observed position versus time is slightly different, shown here. The ball slows down slightly due to friction and air resistance as its points start to go below the predicted points. These points then catch back up due to the ball traveling towards the camera in the z direction. As it travels closer, the ball appears larger and appears to move faster if this is not taken into account. This causes the difference between the two graphs. I have explained these differences here. As I discussed earlier, the computer model assumes that the net force on the ball is 0, meaning there will be constant momentum. This is due to the fact that the computer model does not account for friction or air resistance in this time interval. It also does not have any human error, such as allowing the ball to travel slightly in the z direction. Overall, this is a truly ideal model of the situation. I've displayed this with free body diagrams to the right. The true conditions show that there's an unbalanced force in the x direction due to the frictional force and air resistance force. While the ball still travels to the right, it is slowing down due to these forces as the net force is non-zero. In the computer model at the bottom, all forces are balanced and cancel each other out. This results in a net force of 0 and a constant momentum in the direction of motion. To improve this project next, I could attempt to minimize friction with a ball and floor material that would cause the least amount of friction between them. This would allow the ball to travel at almost constant velocity. Also, I should ensure that the ball travels only in the x component. As the picture shows, the ball slightly travels below the x-axis towards the camera, causing tracking points to become closer together. This caused some data issues as the ball appeared to increase in velocity in tracker. Next, I answer the question, what if the x-axis was flipped? If it was flipped, the ball would be traveling in the negative x direction and the velocity would be negative. This is because the change in position would be negative. This would cause the graph to be downward sloping, as shown here. Over time, position would become more negative. Next I answer, what does it mean? This lab helps us understand that when F net equals 0, any number of forces can be acting on the object to add to 0. This is because forces of the same magnitude in opposite directions will add to 0. An object can continue moving at a constant velocity with any number of forces acting on it, as long as they add to 0. This free body diagram shows that all these forces add to F net equals 0, allowing a constant momentum. In conclusion, the observed position versus time and the predicted position versus time have differences because of air friction, air resistance, and human error discussed earlier. I can minimize these differences, but it's nearly impossible to eliminate air resistance and friction with the tools I have available to me. This lab allowed me to conclude the predicted motion will be the ball traveling with a constant momentum, and the observed motion was a ball traveling at close to constant momentum but slowing down due to the non-zero net force. This concludes my video lab report. Thank you.